Microphone 4 does work. Yeah, it is a most favorite part of all these meetings. Oh, how are you?
How long will this session go?
I hope 1 hour
Okay.
for today. Other sessions will take longer.
Okay.
But today there is basically nothing to do.
Okay.
Maybe I'm exaggerating, but I've checked the code is stable and there is, well, I can try to make it more complicated, but it's even if trying to do some additions, it's quite simple.
You mind share? I'm having not bringing my charger because I don't even use my laptop that much. But
my entire setup at home here. Back and forth every day.
Happy to see you.
There's webcams on these computers now.
yeah, so who added it? Say the cheapest one you're like you make. Those are really cheap. Yeah, right. I got a like 15-year-old pair of heads and hyders that the cushions are like falling apart.
Do you expect anyone else, or it is enough for a good company?
This was everyone that was in the group office, right? Oh, well, I guess we didn't look at the yeah, well, it might have been in the other room. I didn't show.
Well, maybe they will join online or just listen to the recordings. So let's do it relatively quick and finish at 6 if you can. So make yourself comfortable, and I hope everyone has laptops, right?
Yes.
Okay, so just open. Oh, okay. Just open the script I've sent in the email and run it, and we'll chat a little bit about it and maybe do some minor modifications, but it will be basically. Oh, here's Adam. Hello, Adam. Nice seeing you connected. So in the next 2 lectures before your presentations, I should cover 2 subjects on the lecture. So tomorrow, Thursday, and next week on Tuesday, as much as I can stuff in 2 meetings, time-dependent perturbation theory, its solutions, and then projection. What's the right word when one moves software from one platform to another? Migration of the solution from simple here's all from simple two-level system to infinite number of final states or continuous states, and there will be couple of quite well, they're not super complicated, but a little bit exotic solutions. Some of them were demonstrated by London in his 20-second summary of our 3 2-hour total 6 hours of lecturing. So the goal of today's meeting is to in this lab is just to look on the solutions, see how they behave numerically, mathematically, and get some heads up expectations from the solutions that we will be deriving in the class tomorrow and on coming Tuesday. So the time-dependent perturbation theory is one of the simplest chapters of quantum mechanics. So the solution is also quite simple, but we will get through much easier if we will know what to expect as a solution. Of course, I will lose a chance to keep an intrigue tomorrow and say, you do not know what the answer. I want to present it only after like hour and a half of derivations. But if you look on it, you will cooperate better and know what to expect. So the plan, and do not wait for me. If you have the code, just download and run it on MATLAB. I'm just filling the empty space in the timeline with some mumbling, but it's not so important. So run the code and see what happens. And the plan that I want to do is maybe more or less quickly going line by line what it does, running it once for time domain, and then if time allows, doing a bit of modifications and look how the solution depends on frequency of the incident light. And if you want to, I think we just will get fun and intellectual growth by doing it. But if we need eventually give some like points, credits, we can do a little like lab report of collecting all figures that everyone will generate today and send it to me, and I'll give like generous credit for it, calling it like lab report. So did anyone complete it, downloading and running? Okay, let me just walk and see how. Okay, great. Yes, you're ahead of me. I was wasting time on mumbling and didn't run it yet. Screen share. MATLAB. Or maybe I did it at home. Okay. So let's just chat. What do you see and how you interpret it? So let's. On these labs, we have a little bit more relaxed atmosphere, and we do not need to rush through the time as we try to do in the lectures. So we're still in any feedback. What do you see? How do you interpret?
It's
Just tell me anything you see or how you associate figures with. How many lines? What are the axes?
it's the increase in number of given states over time.
Or population of a given state.
Yes.
Okay. Yeah. Thank you. David, you want to entertain us with any verbal description of the figure?
Yeah, there are 6 lines, 1, 2, 3, 4, yeah, 6 lines.
So the red solid, black solid and dashed black, would you think that they represent the same observable in different approximations?
Yes.
Okay, thank you.
Can I say any observations?
And red lines, if you add them together, blue plus red, what do you give?
I mean, the population shouldn't exceed one.
Yes,
Right,
so
so-
blue plus red should be one.
Yeah.
My MATLAB is not currently working.
But you can see it
Yeah.
there or through the shoulder of your classmates. Like maybe 15, well, maybe almost 20 years ago, we had arguing with friends about what is better, Windows or Linux. And in the middle, we decided, okay, enough arguing, let's watch a movie. And the one who was supporting Linux thought, wait, I just need to recompile the core and then we will watch movie on my laptop. So, any feedback on the images that good to see and what you don't see? Of course, I'm guilty for not making the fonts bigger, but
I mean, I see. Yeah, 6 lines, I guess, that, yeah, I don't know.
so
3 of them are increasing, 1 of them is decaying.
okay. And do you see those 2 lines that Hadassah thought should equal 1?
Yes.
How do you interpret them?
Probably as like state occupations.
Okay, yeah, excellent.
Sorry, what would you like to say?
I just have questions.
Okay, oh yes, questions are even better.
So we know what the red is and what the black solid and black dash is. But it does not particularly say what blue is. Is blue just the opposite of the red? So is blue just the opposite of red where it's the
Yes,
evolution?
yes.
Okay.
Okay. Any questions, comments, feedback, impressions?
What does it mean by resonance?
The frequency of the incident light is equal to.
Oh,
the
right,
resonance.
right, okay.
I couldn't hear it because you're not expecting me to say anything. This is so cold. Oh, okay. Just warm up. So what when we were in until yesterday lecture, most of us were living at least in lectures in the world of isolated quantum systems where populations of or initial population of quantum levels were not expected to change. One may get some dynamics because of the constructive and destructive superposition, but energy was a constant all the time, right? Here we do have a population of the like ground state drops, population of the excited state increases, and this happens because of some external perturbation, right? There are several ways to describe this process, and I'm just making a shortcut before we go into details. One is avoid any approximate theories, just propagate wave function for two level system, for 2 quantum levels. One can just numerically follow how the system changes in time. And those are red and blue lines that some of you have discussed. And the solid and dashed, solid black and black dashes are approximate solution that we are going to get in class tomorrow. So if we do not think about quantum levels, if you look only on the three lines, dashed, solid, and red, in the limit when x-axis, when time is small, how would you characterize these lines before they go too far? Which mathematical function they remind you? Yes, right? Everyone agrees. So we are going to practice advanced tool of perturbation theory and get just a parabola as function of time, like t squared. So population at a limit of short time and small perturbations, the population of excited state will grow quadratically. And it will be like big conclusion of 2 hours of derivation tomorrow. So let's, I don't know, go through the code and through the, maybe we will have more than enough equations tomorrow. Let's just go through the code. So please provide me feedback. I'm going to do a silliest possible thing, just going line by line and typing comments. To those who practice MATLAB every day, it is boring and not interesting, but to those who just starting it could be a easy ramp up. Would you permit me to do so, or you are very against? Yes, no? Okay. And if I get tired, I will ask someone takes turns and stop by and type something on this computer, but maybe I will be able, because there are like less than 100 lines. So just clear off and wipe off your images. We are solving time-dependent problems, so we need to have a time step. Since it will be one of the lines is a numerical solution, we need to fix the number of time steps. So some of you did practice wave packet evolution in the integrated PCAM when one has just wave function as a continuously distributed as function of one coordinate or maybe two coordinates, and then running it as evolution operator. And at each point of time, we have value of the wave function in a given point. Here, if we speak about only two quantum levels, we cannot speak too much about wave function. We have only population of quantum levels. So it's a representation of wave function in the discrete representation only as discrete amplitude of wave function for like spin up, spin down, or ground and excited state. And here we define the initial condition for two states. Like ground is 1, excited is 0. And this little apostrophe means that we convert row into column. We'll set up. There is a standard way to perform time propagation. It's like very primitive, basic programming, scientific programming. If we go forward in time, we have a variable that tells us the object that we propagate, the state of the object at a given time step. And as we go through the cycle, we will update and change values. I don't know what are the examples. Like if one is coming to bank and ask what is the amount on the bank account, it will be trajectory of this value. Here is like 2 levels, 2 accounts. So it is, how to say, running or the quantum state that is being propagated. So it will be updated to be propagated. If we want to output results, we probably need to accumulate values of this trajectory, and we need some variable where to store it. So store / accumulate project was. If you want to, like, if you love Excel, probably you don't, but if someone uses Excel or Origin or GNU-plot, there is a big family of software that just reads file with columns of data like X and Y and then plots them, right? So if you have like populations, then we also need time and we need to store it somewhere. Store values of. Okay, here are a few parameters. So since it is a little mathematical experiment, we are not targeting much of realistic systems. So it is parameters, but they can be interpreted. So energy of ground state 0. So h bar equals 1. It means we are in the atomic units, which means that energy is measured in Hartress. Energy is measured in Hartress. Atomic units of energy, one Hartree, is equal 27 something electron volts. So in this just experimental test case, excited state energy is 27 electron volts. The parameter V is our perturbation Hamiltonian, or value of the perturbation, like amplitude of perturbation Hamiltonian. So we can interpret it as electric field times dipole, or we can interpret it as the stuff that we did yesterday, like vector potential divided by C multiplied by mass and stuff like this, right? So it is how big is the interaction, and if it is 0.01, then it is in atomic units, it will be 0.27 electron volts, which means quite frequent oscillations. Okay, so we will see when we do derivations tomorrow that solution does depend not on the absolute values of energies, but on their difference. So instead of absolute values, one needs energy difference between the ground and excited. And through your scientific intuition, it is your question about resonance. Like if the wavelength or frequency of light becomes equal to energy difference between levels, then something will happen. If it is off resonance, nothing will happen, or almost nothing. So this is like an energy difference. So we want to be general. We want to be able to describe not only exact resonance, but slightly off resonance situations. So, and since we are thinking ahead, we like, what if we explore the regular spectroscopy, we explore response of a molecule or atom on the excitation energy. Then we will scan the frequency of the light, and for all values of the light frequency, it will be slightly off resonance, right? So we need to prepare for this and have a parameter that will describe how far we are off resonance. So it's the same as having two parameters and then subtract them, but or we can immediately design a variable for the offset. So how far incident light is off from the energy difference between levels. Okay. And now this uppercase omega W is what we will use as the frequency of the incident light. So right now it is set up to be a little bit off. And then we can either manually change this value, so it is 1% offset, but we can change this value or add additional cycle and rerun the code again and again with different offset and then get an analog of spectrum. Okay. So square root of -1 is imaginary unit. And from now on, we start propagation. So this is integer variable. So L is integer, and by multiplying the integer counter of steps by time step, we get the continuous real, in mathematical sense, time, fractional real. Since we are in atomic units, 1 atomic unit of time is equals, please correct me, I do not, I think it is 1/42 femtoseconds. So I need 42 femtoseconds to get one atomic, no. When it's 42 atomic units of time to get 1 femtosecond. But if I'm wrong, please correct me. Or you may spend a little time in lecturing or working on conversion between units. Okay, so now we populate the accumulation wait values of time. So this syntax in the MATLAB, and MATLAB is most primitive if one think about programming. Some of you guys program something much more advanced, but this syntax means that we take whatever array TT was, and we reassign it to have one more element. So it means like if I put more and more books into the bag, it will become bigger and bigger. Okay, next 2 lines, we set up the Hamiltonian. Set up. So it is not eternal Hamiltonian. It's not universal Hamiltonian. We should note that it is instantaneous Hamiltonian. So, and it is quite important. I'm using this argument. Maybe it's not the best argument, but I'm referring that before, not in your research life, but in our academic life of going through scholar materials, we all were playing with time-independent Hamiltonians, where Hamiltonians set once and forever in vast majority of problems, right? Now we have a big novelty. The Hamiltonian depends on time. It is different at each point of time. So each time step, this cosine omega t gets different value. So here, this V is amplitude of so I would say amplitude of perturbation Hamiltonian, amplitude of perturbation Hamiltonian, but actual perturbation Hamiltonian, perturbation is V equals minus E d times cosine omega t. And it is what we have here. So on the diagonal, we have energies of the ground and excited states, right? And on the off diagonal, we do have an oscillating factor. And we already, if you follow what we do, we do set up the whole script in a way that these oscillations are expected to match the transition energy frequency. But this time-dependent Hamiltonian is what makes the all tools derived before quite useless. So one, as we see it right now, one cannot diagonalize Hamiltonian, find eigenstates, because which Hamiltonian to diagonalize? By if you diagonalize it at each different time steps, it will be different value, right? So through your practice in the time independent perturbation theory, you probably got your own conclusion of observation that the value of the off-diagonal element upon diagonalization just provides splitting for the energies of the original states, right? Agree? Or this sounds surprising? So by in the previous life, in the time independent perturbation theory, if there are non-zero off-diagonal elements, it means your original levels will split. Like Zeeman effect, because there is a magnetic field which gives contribution to off-diagonal part of the Hamiltonian. Yes? I just do not see big enthusiasm. Maybe you hate time independent perturbation theory so much because of homeworks and you do not want to remember this experience. Okay, but now if we apply our thinking of the time independent perturbation theory, we should look on the levels of this two-level system being like they're already split, they have transition energy, but per additional off-diagonal element will split them further or closer, right? So if we diagonalize this 2x2 Hamiltonian again and again at each point of time, it will be a little oscillations of the energy of ground and excited state, right? And then the eigenfunctions will be slightly different. So it is possible to do, but it is very cost inefficient solution, because to get high precision, we need to perform this diagonalization again and again at each time step. And there are better ways. Okay, does it click something? Please tell me if it makes sense. It doesn't make sense, or you think it is very boring. I don't care. Okay. Okay. So let's continue. But this is we will have no time to go over this little part on actual lecture material, but it is kind of cornerstone of the thinking. Like in textbooks, it is assumed self-evident. Like if we start time-dependent perturbation, we are suffering of being unable to solve problems with time-dependent Hamiltonian. And it is the main reason to do these things. Now, if time step is small enough, then we can numerically propagate and find next what would be the wave function at the next time step, just by using evolution operator. Evolution operator. Operator, which is nothing but imaginary unit divided by h bar, which is 1 in this, then Hamiltonian, then time step. Are you okay with solution operator, or someone hates?
So EXPM is exponential, right?
Huh?
That's like the.
Matrix exponential. I'll probably type it here. Like if we do exp of a matrix. Yeah, probably I need to show it on the blackboard. It's too much for typing. So I'll stop sharing and do little note on the board. So if you do exp of then you'll get E11, E12, E21, A22. But if you do EXPM of a matrix, I'm lazy to write it down, the same matrix. It is computed as identity matrix of the same size plus the matrix in the first power plus the matrix times itself divided by 2 factorial, and then continue the Taylor expansion of the matrix. So it uses multiplication of matrices, and result will be different. And if we really want to deal with quantum operators, then we need to do matrix exponential. Here. Okay. And as soon as we have defined evolution operator, we can find the wave function at t plus delta tau will be the wave function at in the past multiplied by evolution operator. Well, I don't know how to explain it, but it's the same as written there, right? So you just propagate it forward in time, but you store the result of this evolution in the same variable, right? Store in the same variable. Store in the same variable. So why we should believe, why we can believe this evolution operator and this way of going forward in time? Okay, let's do a few more notes. And I believe you all know it. I'm just doing a little recital. So why evolution operator gives us the future of the wave function? Just think inside yourself if you can come to the blackboard and justify it. I promise I will not call you to come, but give me a little sign if you think you could do it, you definitely cannot, or something maybe. Okay. So it's like a dial clock. So it's no one shows completely polarized. It's like different degrees in 50%, 75%. Right? Not sure. Okay, so we all are taught to believe in Schrödinger equation, right? d dt psi plus minus I h bar h psi, right? So what if we integrate it? So you'll get psi of integrated from t0 to t0 plus delta t. You'll get t0 plus delta t minus psi of t0 on the left, right? So integrating the derivative, you'll get the function itself. And if you take limits, you'll get this. Catch me if you can. I like if errors are code. And here we just have the integral from t naught plus delta t h psi dt. And if we integrate this, if dt is small enough, it can be just minus I h bar h psi of t naught times delta t, right? Right? You still believe it? So we can put this one, keep it on the left. This one will go to the right, and we'll have psi of t naught plus delta t equals psi of t naught minus I h bar h psi t naught delta t. It doesn't look yet as a time evolution operator, but we can put the psi naught away from the brackets. So maybe to the left. So 1 minus I over h bar h operator dt bracket psi naught of t equals psi of t naught t plus delta t. So if time increment is small enough, right? It looks like first two terms of the Taylor expansion of exponential, right? And then we can replace this 1 minus I over h bar h dt to the exponential. So e to the power, everything was here goes into power of exponential minus I h bar, Hamiltonian, delta t, and here we have psi t naught, right? And then we have propagation from near past to near future. And this exponential is what helps us to go forward in time. It's just a little bit more reliable than linear thing because it automatically includes higher order corrections and it practically works a little better. Okay. Yeah, I probably was too optimistic about 1 hour, but trying to. And then after the propagation, one step of propagation is done, we need to accumulate trajectory. So here psi at each time step, psi is an experiment type. Psi is the column, is a vector, column vector with 2 elements, right? In their complex. And if we do this accumulation command, we just grow a matrix with 2 columns and as many 2 rows, because each column, and so many columns as many time steps, right? Each time it grows a little bit more. And then at the end of the cycle, we do have trajectories stored at this all psi and TT. So the result of the perturbation theory that we are, it's my duty to derive tomorrow, will be to show that it will be, so wave function will be equal the value of Hamiltonian plus two terms that include both exponential and denominator offset value. Right now, it's not our task at this meeting to derive or justify anything, but you see that if the offset comes into denominator, as soon as offset gets smaller and smaller, the overall response of the system becomes bigger, right? So it is facilitates answer, and if you get it absolute zero, then response should be like infinity. And there are two symmetric terms, one where energies are subtracted and another where they are added together. This is what will be prompted and dictated by first order perturbation theory. And I believe we all have seen these equations in one slides last Friday, right? Something along this notes, like exponential in the numerator, a subtraction of energies in the denominator, and exponential is time dependent. So one of the very little derivation that we will repeat in the class tomorrow, but maybe we can do it even right now. So let's look on the highlighted thing, and I will reproduce it on the board and give a little comment. So if you do have exponential minus I, here we have time that is running through all values. And then we have energy offset minus frequency. Here we will have -1. And in the denominator, we will have energy offset. If we do not decline units, it should be no H bar. Frequency 1, 2 minus frequency of light. So same game as we did discussed several times by now. The exponential can be considered as 1 minus IT omega 2 minus omega. And then, so the first order in the Taylor expansion of the exponential, right? And then one can tell plus t squared over 2 omega minus 1, 2 minus omega squared, or so forth. And then here we have -1 from the equation that we are going to derive tomorrow. So here we have 1 from Taylor expansion. Here we have 1 that we are going to derive, right? So this one and this one are dropped, canceled. And if we consider time limit going to 0, right? Then we will drop terms higher than first, right? And the denominator did have omega 1, 2 energy difference minus frequency. So then we can cancel the offset of energies, and then the result will be minus IT, which is imaginary unit and time, not the information technology, right? So this will be solution for population, not population, the expansion coefficient of the excited state as function of time. Like if our wave function is ground of t times ground wave function plus excited of t excited wave function, then and here one should also have the value of coupling, then wave function expansion coefficient will grow linearly, right? And if we need population, if we need absolute value squared, then it will grow quadratically, right? So basically it is the goal that we need to derive tomorrow, right? And we are going to, well, it is what this code generates as a reference point. So the exact quantum solution is a reference point because it's so easy for simpler system, and other two lines, dashed and solid, are perturbative solutions, which are like discovery. And they are more universal because they can be applied to any to very large systems. Well, for exact quantum solution can be done only for few. So this is time-dependent perturbation theory solution of the first order. And what are the solutions for here? So adding together these terms, and how do second or infinite order solutions look like? We'll learn from London in one day and a weekend one day. Okay. So and here is the thing that we just discussed on the blackboard. So what would happen if we apply Taylor expansion, Taylor expansion of TDPT solution? So see that it is just imaginary unit at times time. So expansion coefficient grows linearly. And if you do want to plot observables, we can generate as like wave function expansion coefficient conjugated times with wave function coefficient itself will be population. I've promised that it would take 1 hour if someone has some duties, responsibilities, and need to leave. Go ahead, it's okay. But you went through main part, and now you will just rerun the code and see. But it was the main part. So population of ground state, population of excited. And here, I don't think we reported, but it is this PX, PY, PZ. We are not plotting them, but it is something you probably played a lot in the first part of the course, where you extracted the spin projections out of the two-level wave function, right? If you take expectation values of Sx, Sy, Sz operator in the basis of two-level system, you get this manipulations, these combinations of the expansion coefficients. So same for perturbative. In the earlier lines, we get this perturbation theory for psi and for wave function, and here we do need the population. And here, this solution is where we get just linear increase with time. It is correct only in the resonance condition. So it is Taylor expansion. But it will be correct only if in numerator and denominator we have cancellation of energy. So it will work the best in the resonance condition. If we are a little away, it will be less and less practical. And then we plot several things. So here we have population of ground, population of excited, time, and perturbation. So we may and hold on means we keep image in place. So let's maybe do it once again by copying the line, declaring new figure, and so this solution comes from the time evolution operator, which is numerical correct. It's not analytical, it's numerical. And what we see here, it is a literal demonstration of what is the perturbation in a scale. So it is about 100 times smaller than the energy difference between ground and excited. And it oscillates very frequently. And as a result of applying this interaction with light, we do see that the population of excited is growing and population of ground is decreasing, right? The interesting thing is just to observe that the rate how population is changed and eventually it will oscillate, and the rate of the basic frequency are very different. So in optical experiments, this frequency is of the order of 1 femtosecond, and rate of how the population is changing is of the order of nanoseconds, like several, not 3, even sometimes 6 orders of magnitude different. Okay. And then the single solid line does show the result of perturbation theory, and the the dashed line does show the Taylor expansion, which works well in the resonance. Okay, so when we run it, we get this several lines, and I would like to invite you to make copy paste of this figure and just provide maybe a couple of lines explanation as a report of our lab. And there is a little creative task is to show how the amount of transferred population, basically how high is the red solid and dashed line, depend on the offset, which can be done in 2 ways. Just use the same code, manually change the offset, rerun and store it in a table, or modify a code and make it going in a cycle and storing the information. So let's set up due date maybe before next lab, a week. You can complete it at home. I'll try to formulate and send a reminder email. If you want, I will probably try to program it myself and see like if I can reproduce this thing myself. But I do not want to hold your time because we've got enough information. So any questions or objections?
I have a question on the syntax for plotting. So you can plot multiple things in the same plot function, so you can plot a variable.
Yes. Yes, you do. If you have like functions y1, y, and y2, and the same x for both, you do plot x, y1, x comma y1 comma x comma y2 comma, and then it will be two lines. Okay.
Do you need to say, like, do you need to create the figure explicitly though, if you're gonna put multiple plots on the same, like multiple graphs on the same plot? I think that you have to do that in that lab. But you have to just basically say figure, right? So that it holds the figure, like,
Cool.
and then you keep plotting more stuff onto that figure.
Hold on means yes, it will be just accumulating stuff again and again. But
Is you do not have to explicitly create the figure. It's highly recommended.
Okay,
so what I consider as a little exercise, whatever homework report, is to let me bring it back to the screen. So you see that they start to diverge, right? It's not anymore quadratic or linear, but they both go quite high, and the quadratic definitely exceeds 1, so it doesn't conserve probability, right? Which is okay if you assume that coupling is small and time is short. It's okay. Here they coincide. But what I'm curious, or what is like our homework, I'll try to do it myself to create maybe an answer key, to check how do the height, like if I select maybe height of each of the line at value time equals 100, or maybe at times equal to 100. So how this height of the red line depends on the value of uppercase W, on the value of offset. And the same for other three things. So what is expected to have something like a resonance function with like Gaussian, delta function, Lorentzian, or maybe something a little bit more different. Basically, we will see it in class tomorrow, but if you pair it with a little personal exploration, it will be a good complement. So it should be something that will peak dramatically when the frequencies coincide, and will drop in some way when it is off resonance. And the simplest way is just let me show the simplest but not the optimal way. So we do have the so we can number T steps. So here is the whole array. You see it, it grows smaller and finally it approaches 1/2. And if you take the value of P2 in T steps, it will show this one. If I take the script and take that offset, will be 2% instead of 1. Save, we run. So you see figures show dramatically and the discrepancy changes. And here I can do P2 and T steps, and it shows instead of 48% population, it shows only 12% population, right? And I can do like 20 or 40 times depending on if I'm workaholic or I save my resources and save this data in the column that plot either with MATLAB or with Excel, and see that it is a resonance. And we see that it will be resonance, right? An alternative way is just to make wherever this offset is described to type something like 4 offset equals from -0.3 by step some small step to 0.03, maybe a little bigger. And repeat everything and just speed off the values, whatever you find more reasonable. Okay, and get the resonance curve. So I was trying to promise that we will finish in an hour. Everyone is welcome to depart and disconnect. But if you really have steam and intention, say you can try doing this little exercise here, but it's not demanded. I can sit, watch and assist, or try doing it myself. But I think before we get too far into this half semester, we can, it's your choice, like accumulate energy, relax, and prepare to stress at the end, or invest a little bit more. Now I'm fine either way. So let's vote. Anyone plans to depart immediately? Okay. Anyone is interested to stay and chat a little longer? Can stay, but not really enthusiastic. Like can, but not really wishing. Okay. Yep. But where is the camera? Formal part of meeting is done. Everyone is welcome to disconnect and depart. The rest is how to say, extra activity. Steven, any questions about the content or your?
Not really.
Okay.
I was trying to get a concept. So you said this is the entire system.
Ground state.
So I was trying to get a concept. Which sense is the first of activation?
Mhm.
So I was just trying to like. It's still like a line.
No. Thank you, Patricia, for formulating this question. I don't know why our images are so small. Yeah, this is better. That's so Patricia was looking onto this trajectories, and she was asking. I like your question. I'll just try to reformulate it. The answer is no, but the logic that you're trying to practice is very natural. So there is a confusion when doing a transfer from time-independent perturbation theory and time-dependent perturbation theory. And we all are, how to say, under pressure, under brainwash of the time-independent picture when we see that perturbation splits the levels, right? And when we see a figure when like something is also changing as we change parameter, it goes in a wrong association that with a perturbation, energies of level must differ. No, energy levels are the same or they're just slightly oscillating. We do change population of level. So like population jumps from ground to excited, but not instantaneously, not 100%, but like a little by little, right? So there is a probability. Initially, we have 100% probability that system is in the ground, and 0% probability that it isn't excited. As we go forward in time, this probability distribution is changing. So a function will be new, will be different at each time step. The perturbation, it is time dependent, but it is regular. We in some sense, although it oscillates, we have the same perturbation. But same perturbation makes continuous dynamics of the populations, of the occupations. Does that address your question? Many thanks for asking. It's really good. We got it. Element Hall did departed. So do we really want to do more effort in programming, or especially London, you just draw a code in your head, run it, and just spit out the numbers.
I think that like is trying to do like a full MATLAB install because it's only like 14% done rebuilding it. So I'm trying to do like all of MATLAB instead of just like the core of it.
Right. The core is well, if you already started, it's fine. But the core MATLAB is something that was basically complete and ready to use 30 years ago, and the full mat that was working on computers with 20 megabyte of hard drive. Right now we have images of 20 megabytes or
Yeah.
right. So when I was an undergraduate, it was considered as a wonder. So it was a transition from floppy disks of 500 kilobytes to a 20 megabytes hard drive, which was like, oh, one can store the libraries and codes and everything and games and then be a king. The new, the full version of MATLAB includes artificial intelligence to driverless cars or driverless drones. It has some face recognition or how to optimize spendings in a big company. So or how to map volcanoes in the area. So some exotic applications that I'm not sure if you will ever use.
Yeah. But I got that on this computer now.
Oh, okay. Okay. But I think you have an idea what to do, right? How to do this.
Well, yeah, so like what was like the assignment again? We're just trying to like
Find-
describe the dependence of these guys on.
Dependence on like this point,
Yeah.
heights of this point on the frequency omega of the incident light.
Okay.
Like if we tune the external light source to exactly match or slightly offset, and how far the rate of this transfer from ground to excited changes as we go between as we have smaller or bigger offset of energies. Okay. There is an interesting comment that I just set sharing over again. There is an interesting comment that I was inspired by Patricia. And it does relate to the subject that London has selected for presentation in a weekend one day. So when time is small, first order perturbation coincides with the numerically absolute solution, right? But as time increases, they start to diverge. And well, if you go away from this quadratic function will never flip over. It's clear. So very primitive. But here we also have increasing discrepancy because the absolute solution includes all orders of the perturbation theory, like first, second, third. If you would include like first and second, it would be in between these two lines. And if you include like third, fourth, it will approach closer and closer to numerical absolute correct solution. So if in some problems it is possible and it is beneficial, but for practical applications it is too much work without much benefit. If you go in, if you do not sit inside a resonator of a laser, if you just do a spectra of molecules, absorption and emission, we are in this limit, and first order perturbation theory would allow us happy and prosperous life until retirement. David, are you,
Reading papers.
so you're not planning to like do this little programming effort? You think
At least not right now.
you'll do it on your own? Sorry?
First thing you said they wanted to.
Okay, so you just support the company. Yeah, if you find this little effort of completing task is hard, just send me emails. I'll cooperate. Patricia, is it okay to do it
Yeah,
on your own?
try it now, but I don't know how to do it.
Huh?
I'm trying to know, but I don't know how to do it.
Do you want to do like simple way or or advanced way? Okay. So I'll just say a couple of words to Patricia and then probably we'll dismiss absolutely. So change this number. Save and rerun. You see, the picture did change, right?
Yeah.
Okay, and now we do need the P2 of T. So your offset. It's my typo. Doesn't recognize, but so you make a table. In one column you do offset, in another this P2 of T steps, and you accumulate as many data as possible, and then just plot them one against other. Okay.
I have a very dumb question.
There are no dumb questions. There are dumb answers.
Okay, I wanted to ask here, I just wanted to be sure that like there was a place you used the values of perturbation 0.01.
Mhm.
Here, so that's a different value.
Okay.
I just wanted to ask that, is it because this one is an atomic unit?
Yes. So in atomic units, one atomic unit of energy is 27 electron volt. 1% in atomic units of energy is 0.27 electron volts. So done.
Is it possible to get the commented version?
Oh yes, I'd be happy to share. I'll do it right now so that you will get it immediately. Let's save it as a. Okay, done.
Thank you.
So do I have a permission to stop the recordings and dismiss absolutely? Okay.